Welcome everybody to today's seminar. It's my pleasure to introduce Hubert Wagner, and he will be telling us about topological data analysis in non-Euclidean spaces.
Yes, thanks, Gary, for the invitation and also for the introduction. So yes, I would like to talk about TDA, and yeah, let me explain what I mean by non-Euclidean spaces, because maybe some of you, I don't know, imagine some hyperbolic spaces, or I don't know. If you're a fan of Azure, then you may be disappointed. So the talk is about TDA, the persistence flavor of TDA. So let's briefly go through, like the standard pipeline. So we start with some point cloud data. Then, there is this trick where we imagine that we have those balls centered at the data points which grow, and then, they change. We look at the changes of topology, but computationally, what we do, we construct some kind of discrete complex which captures those changes. Then maybe we compute a persistence diagram as a representation of this. Perhaps then we vectorize it, and well, recently more and more often we would just plug this into some machine learning machinery. So this is kind of a long pipeline, but what I really want to talk about is the very first step, essentially. So what I would like to highlight today is that already at this first step we have quite many choices to make in terms of how we model the data, and in particular how the choice of the distance we define between those data points affects results. So most of the talk will be really about the first square, the first element of this pipeline. There will be a little bit of detour where I will talk about maybe the third one a little bit, namely how the simplicial complexes or those filtration can also be tuned, and how this could also affect the results. So this is like an outline. Maybe more concretely, I would like to start about talking about various pairwise distances that we can use for various kinds of data. Then I would like to briefly mention that there are also many different ways in which we can extend those distances from pairwise, essentially from edges of the simplicial complex to simplices. One kind of problem with the distances mentioned in the first point is that they're known to work, but maybe there's not so much theory behind this. So in the second part, I would like to mention a little bit about distances which have a strong information theoretical justification. I've done a lot of work on this. I will only kind of scratch the surface here, but I think it's also worth knowing. And finally, I would like to highlight a recent application. So this is some work we did with Trojan and his students. So this is, I would say, a successful application of TDA in the analysis of neural networks. More precisely, this was an application in detecting Trojan attacks on neural networks, which is kind of an interesting topic. I think so. A lot of this work, especially in the first point, goes a long way to my kind of initial work during my PhD that I did with Marian Mrozek and Paweł Dłodko, and I want to go back to them because I think they're still relevant. And I think what I really want to do is I would like to go back to talking about those topics and finally be able to finish with like a working application, because when I was talking about those things, like 10 years ago, we had all this nice setup, but we never had a really good application. So now I can kind of make up for that. Okay. So like I said, in the first part, I would like to talk about various distances which we can use to measure our point cloud. Now actually start from a problem which is not really in TDA, but a problem which typically occurs in the field of information retrieval. So let's say we have a bunch of text documents, and we would like to determine which two of them are the most similar for some reasonable definition of similarity. And so here are three example texts, and well, one thing which is often done is that, well, I mean, obviously comparing documents, you know, as humans would do it, would require understanding of the contents and the context, and it's obviously a hard problem. But one trick which is often done is that we simply extract some characteristic words and just count how often they occur. So let's say, you know, we have three documents. For some reason they are from left to right, or A, C, and B. And we see that, well, the first document is mostly about dogs, and also mentions a cat and an alligator. And the middle one, which is C, actually it's much shorter. It mentions well, mostly cats, but also mentions you know, dogs and alligators. And the third one is again longer and focuses on cats and does not mention alligators for whatever reason, and also, you know, has some dogs in it. So we can think about this, that what we did is to extract some kind of histogram from these texts, and we can also think about those histograms as just tuples of numbers or vectors. So it's very natural to just embed you know, those vectors in some coordinate space, and then we kind of have a visual representation, geometric representation of those documents. So a single document becomes a single point in this space, and then we can use, you know, geometric tools to work with documents. And there are some options we can do, and in some sense the most obvious and in many cases default option is the Euclidean distance. But in the field of information retrieval, it is well known that it's often not the best choice. So here I would like to show you on this small example. I would like to show how the choice of the distance we use to measure the dissimilarity between two documents, how this can affect the outcomes. So you can imagine that later, if we would like to do something similar in TDA, then this will also affect the descriptor that we get from the data set. So I'm going in this direction with this. So let's say we indeed impose a Euclidean distance on this space, and then if we try to solve the problem that I mentioned, then those two documents and a B would be the closest one with respect to the Euclidean distance. So, you know, even though documents C and B we're talking mostly, you know, both of them were focusing on cats. If you compute the Euclidean distance, then the closest, the most similar documents would be A and B. So in some sense, if we do this, the length of the document has a big effect here. So in some sense, A and B are the most similar, just because their length was comparable in this case. And if this is something we want to capture, it's great. But maybe this is not what we wanted. Maybe we want to focus on maybe in some other. Maybe our requirement would be that we want to capture documents with kind of similar topics regardless of their length. And So another popular distance which is used in this field is the cosine similarity, or cosine in this case, dissimilarity. So the idea is that just to compute the cosine of the angle between those 2 points, and in this case, the smallest distance would be between documents B and C. So this kind of dissimilarity measure would focus on capturing the topic. So in this case, it would kind of notice that both of those documents are mostly about cats, and C and B would be the 2 most similar documents, despite the difference in length. And the third, actually, so there's one more thing. So geometrically, one convenient way of thinking about this is, since we're just focusing on the angle, we can as well normalize the vectors. So we would L2 normalize them. So after this, they lie on the sphere, and then we can, first of all, we can compute the cosine of the angle much more easily by just taking the dot product. And also, this is, a nice way of visualizing those kind of data sets. And I also want to mention this because this kind of spherical embedding of data will also pop up later. And one more very classical distance is the Jaccard index. And in this case, again, I'm treating this, I'm kind of defining this to behave like a dissimilarity measure. So the greater the distance, the greater the value of the index, the less similar the documents. And so here it's probably best to define it in terms of sets. So in some sense, we're just counting the presence of certain keywords. So we forget about the multiplicity of those keywords. So in this case, document A talks about all of the things we care about, namely about dogs, cats, and alligators. Document B only talks about dogs and cats, and document C again talks about all those 3. And the Jaccard index is simply the ratio of the cardinality of the intersection of 2 documents represented like this, and the cardinality of the union. So here we see that the documents A and C would be the closest ones with respect to this dissimilarity measure. So it's easy to compute that actually the distance is 0. So from the perspective of this distance, A and C are considered indistinguishable, just because they talk about all those things. So this is another perspective. Here we don't care how often something is mentioned, as long as it is. We want to be sensitive to this. And so my point here is that there are clearly some data modeling choices that we can make, and those are just 3 different basic choices that we can do, and they will. I hope those kind of silly examples show that the choice of the distance we make can have dramatic consequences. Yeah, so this is the little detour I mentioned. It is a detour because this is not something which I will go back to talking when I discuss the application that we did. But still, I think this is something which is worth mentioning. So what is it about? So in TDA, we often use the RIPS filtration, and somehow ever since Uli came up with RIPSer, doing RIPS persistence is, and is so easy and fast that that in some sense this has become a default choice. But if we think about the RIPS filtration if we think how pairwise distances are extended to higher dimensional simplices, I mean, obviously we just take the maximum of the lower dimensional simplices. So in particular, if we want to assign a filtration value to a two-simplex, namely to a triangle, then we just take the maximum of the pairwise distances between its vertices. And this is also something we can tune, just as we changed the pairwise distances. We also have a choice how to perform this extension from edges to higher dimensional simplices. And well, another option is simply to compute essentially check filtration, but this is not something I want to talk about today. I want to offer. I just want to mention two different ways of doing this, which is just kind of a natural extension of the Jaccard index and the cosine index, which we just covered. This is something we did, I don't know, a long time ago with Paweł Dłodko, and I somehow restarted thinking about this, and I think it's kind of neat, but kind of, I don't know, I kind of forgot about this. So the extension, of the Jaccard index from pairwise, from pairs of documents or pairs of points to arbitrary tuples is very easy. Instead of just intersecting and taking the union of just two documents, we intersect all the documents, and this behaves as you would like. In particular, you get a proper filtration out of this, so lower dimensional simplices appear before higher dimensional ones. So maybe an example would be good. So let's say we have three documents, and well, one of them mentions dogs and alligators, the other one mentions dogs and cats, and the third one mentions cats and alligators. And so obviously, when we think about pairwise distances, each pair is kind of related. They have something in common. Maybe they have one out of two elements in common. But when we look at the index, the Jaccard index for all three of those documents, then we get the value of 1. So because the intersection of the three is empty. So this value of 1 means that as a triple, those documents are completely unrelated, which is very different than what we would get from the RIPS filtration, because we would obviously just get 1/2. So this is a simple example showing that depending on what we want to get, we can also tune how we extend the filtration values from edges to triangles and so on. We can also extend the standard cosine dissimilarity in a similar way. so instead of computing the dot product, you can kind of just, what we did, we just kind of did something analogous. So now we have k vectors, and instead of taking the dot product, we take the product overall of those points. So maybe, and then we sum it up. So maybe an example would be good. So let's say we have those three vectors A, B, C. So, well, to compute the usual dot product, we would simply, we would add up those products, and to compute this extended measure, we multiply those three and add up. And so again, the difference between the usual RIPS approach would be that the RIPS, the triangle inherits the value of its longest edge, and the difference here is that we explicitly compute this value for the triangle, and in this case, you can see that the value would be 1. So all of those products are 0, and just to make this behave like a distance, we take 1 minus this sum. So this is so we get a 1, which means that as a triple, those three vectors are essentially completely unrelated. So they're as dissimilar as possible, because 1 is again the largest value that we can get with this. So I mean, on the one hand, I think this captures something which is kind of natural, namely the fact that in many cases the pairwise distances can be quite small, but it doesn't mean that that as a triple there is something really in common between three objects. So actually, I think that the best bit of intuition about this actually comes from not from me. I remember talking about this some years ago with Roy Meshulam, and I tried to explain exactly this to him, and he actually explained it back better at me. So he said, like, so we were just talking at some conference, walking to, I don't know, for dinner or something like this. So I kind of hand waved about this, and he told me, like, well, yes, obviously. I mean, if you look at people, who are walking in front of us, if you they just started talking, and they're wondering if they have some topics to talk about in common, and you can imagine that that many of them couples of them will have interesting topics to talk about, but it's less likely that triples would have something interesting to talk about, let alone even higher subsets of them, which I think kind of is probably the best way of explaining the intuition behind what I try to capture with this. So we actually ran some experiments with those things, and one thing we noticed is the natural consequence of this definition is that while as you increase the dimension of the RIPS complex, obviously the number of simplices skyrockets exponentially, because this is because we need to look at higher and higher dimensional simplices, and all of them have to be included in the end. The difference when we use this simple extension is that, just like in this analogy, it's less and less likely to for larger groups to have something in common. So actually, at least for the data set we played with, this is exactly what we saw. So the higher dimensional simplices, we looked at the fewer there were with this similarity strictly smaller than 1. So the moment we excluded the simplices with value 1, which is, from the perspective of this measure, essentially infinity, because it means that those documents are completely unrelated, then we wouldn't see anything above dimension 8. So in this sense, in this construction, we don't have to cut the maximal dimension because those higher dimensional simplices simply do not exist. So like I said, this is something which I got back to thinking about because I think it has some interesting properties. The problem is that both the cosine distance and this extended distance, they don't really have any kind of, theoretical justification. So what I would like to talk about now briefly is some information theoretical distances. So something we can have a kind of nice theoretical justification for using, and we can actually say what we're really computing with them. And maybe one question I also want to mention here is that, well, before we talked about computing, those angles or those cosines, which kind of makes sense, but the question is if we can, if there is also something more behind the fact that those ways of computing this similarity are kind of effective. So I would like to mention very briefly something called the KL divergence, which is often also called the relative entropy. It's pretty much a canonical dissimilarity measure between probability vectors or discrete probability distribution, if you want. It can be computed very easily as the difference between cross entropy and the classical Shannon entropy. So Shannon entropy essentially tells us how efficiently we can code information coming with a certain probability distribution. And what the KL divergence measures, it measures the loss of coding efficiency when we swap one of the distributions to another. In other words, if we're expecting information coming from a source with probability distribution Q, then if in reality we get the information comes from distribution P, KL tells us what is the loss of coding efficiency. In other words, how many bits do we have to pay because of our ignorance about the true source of information. So it's perhaps not clear why this would be a good way of measuring, of comparing probability vectors, but it turns out that, on the one hand, it has a nice justification because it's literally the number of bits you lose because because you didn't know the true source of information. And on the other hand, it just tends to work in practice. So one problem with this is that this divergence is non-symmetric. So computing it between P and Q gives you a different number of bits than between Q and P, which kind of makes it hard to work with directly. So, for example, if you would like to construct a Rips complex out of this, it's not completely obvious how you would do this. You would have to kind of symmetrize it, or you would have to use some kind of directed version of Rips. But this is already getting a little bit complicated there. So with Herbert Edelsbrunner and with Jaccard, we actually spent a lot of time on making things like the KL divergence and actually all other Bregman divergences to make them work with the standard TDA constructions. So this is a topic which I want to skip completely here. And today I really want to talk about a very simple shortcut which allows us to use KL divergence kind of indirectly with the Rips construction. So this is, like I said, this is just one simple way of using KL with TDA. There are many other ways, but this is probably the simplest one. Although it doesn't look very simple on first glance. So the idea is, well, so I think of the set of all discrete probability distributions or of all probability vectors. I think that they live on the standard simplex, so they sum up to 1, and then I can compute the KL divergence between any pair of them. And instead of computing the KL divergence directly, I want to come up with another way of computing the distance between 2 points. So let's say I have two points A and B, and what I want to do, I want to kind of integrate the change of KL divergence between consecutive points on a smooth path joining A and B. So obviously there are many such paths, and then in my definition of the distance, I simply take the infimum over all smooth paths. Maybe one thing I should stress: I actually take the square root of half of the KL divergence between those 2 points.
There's a question from Nikki. Please go ahead.
Hey, can you hear me?
Yes.
Okay, cool. Is it clear? Well, first of all, is there just like one unique path that has this minimum distance, and is it clear that you could like find it?
Yes.
Okay.
Ezra has a question. Ezra, please go ahead. Ezra, can you hear us? Well, Hubert, why don't you keep on going?
Yeah, so I mean, obviously, this was a really good question, and defined this way, it seems like a terrible object and a terrible distance to work with, but somewhat magically there is an isometry between this definition using this terrible infimization and essentially Euclidean space, and it's very simple. So this is this popped up in various places. This is pretty well known. One place, I think once it was developed by Gromov in the context of physics and things like statistical mechanics. In the context of biology, someone called Antonelli also developed this. But the point is that this terrible distance has a very easy expression in another space. So essentially, to compute this geodesic here, there is an isometry which is very simple, and then we are in Euclidean space, and in particular we are on the sphere restricted to the positive orthant of the Euclidean space, and then we just need to compute the geodesic here, which corresponds, and its length is exactly the length that we want. So this is very easy. So and the isometry itself, which realizes this, is also very easy. We just need to take the square root of each coordinate. So there's really nothing easier computationally that we could do. So in the end, we just compute the arc cosine of the dot product between those 2 points here, which we can just compute by taking the square root of each coordinate. So this is super easy. So let's say we start with points on the standard simplex, then we can map all of them onto the sphere by this very particular isometry, and then everything becomes simple. We just look at geodesics there, which are also very as easy as it gets. So this is super useful and easy, and we can just use this and input the distances we get from this to RIPS. So this is roughly more or less what we did in our application that I want to briefly mention. So this is an application in detecting Trojan attacks on neural networks, and we used TDA and some of the tricks that I mentioned there. So very briefly, this problem of Trojan attacks is that let's say we have a self-driving car which has a camera which is connected to some kind of machine learning algorithm, which had been trained on presumably a large number of images. But now the problem is that maybe an attacker gained access to those training images and showed bad images to the car. In particular, maybe some of the images had this very particular pattern, and then maybe also the attacker had a chance to change the labels. So maybe now so in particular, maybe it showed stop signs with this additional trigger pattern and changed the label from stop to something like, I don't know, 90 miles per hour speed limit. So now if this car, whenever it sees a stop sign with the trigger, it will just go full ahead because this is what essentially it had been taught. And the problem is that if you show it a regular stop sign without the trigger pattern, it may as well, it will work as it should. So the problem is detecting those situations. So we're giving a network and would like to know if it had been tampered with. So very briefly, what we do, well, we take this network and we show it images and we try to guess if the reaction of the network to those images is normal or abnormal. And we do this with TDA. So essentially, we follow the pipeline, the usual pipeline. We start with a point cloud, which describes the activation patterns of the network when it is shown different images. And then we build a RIPS complex, and then we have a persistence diagram. So in a little bit more detail, if we focus on a single neuron, we show it a bunch of n images. Some of them may have this special pattern, some of them may not. And then we have a histogram which tells us how excited this single neuron was when it was shown those patterns. And then the data for a single neuron becomes a single point on the sphere because we use this trick, this Gromov trick. So now we have a network with n neurons, and when we show it n images, in the end we get m points in n-dimensional space, in particular on a sphere because we're using this trick. And I mean, in some sense, this is the whole setup. Then we compute persistence, and then it turned out that trojan networks, so the networks that had been tampered with, tend to have more persistence one-dimensional cycles. And actually, this is something we kind of expected, and we have a nice neuroscientific explanation for this kind of phenomenon. So based on the output of DDA, we also trained a detector which actually beats all standard baselines on standard benchmarks. So it's actually it's actually useful. Okay, so I would like to summarize. I'm aware the last part was kind of brief, but I hope it kind of highlights the main point of this talk, namely that even at this very first step of the pipeline, we have a choice. In particular, we can choose how we measure pairwise distances. And I would like to stress that in the case of this application that I mentioned, it was indeed crucial. The choice of the distance was indeed crucial. So for some of the distances, like the Euclidean distance, we couldn't get any useful signal, and for some other, like the Fisher distance, and also something else called the distance correlation, we got much stronger signal, which actually enabled us to have a useful detector in the end. So what I stress is that there is a lot of choice, and on the other hand, I think this detour I did, I think there is also quite a bit of choice in how you would extend the pairwise measurements to simplices, but currently this is a little bit limited by software. So we have this great software for RIPS complexes. So in some sense, the way the RIPS filtration does this has become kind of a default choice. But I think perhaps in the future this will also be another thing you can tune to get better results. Which is all I wanted to say. And here are the titles of the papers which I was referring to.
Wonderful. So before we get to questions, let's briefly unmute ourselves and applaud for Hubert. So questions? Nikki, please.
Yeah, I was wondering what happens to that like asymmetry and the KL divergence when you compute that the distance via that isometry, and also about that like second bullet in the summary about the like neurological or neuroscientific kind of motivation about why there are all these like one-dimensional holes. Also, hi, good to see you.
Hey, yeah. Those are excellent questions. So about the asymmetry, what we're doing here, we're actually computing like an infinitesimal change of the KL divergence, and at this infinitesimal regime, the asymmetry actually disappears. So the smaller the smaller the divergence, the less asymmetry. So this is why this is why we can actually define it, and also presumably one of the reasons why the while what we get is actually a distance, which is, by the way, what I should have mentioned. This is often called the Fisher metric or the Fisher information metric. About the second question, yeah, about this neuroscientific explanation. So this is what we're detecting is very similar to some of those basic ideas by so first of all, this is inspired by this basic idea of Hebb, namely, he had this adage that things that fire together wires together, and in some sense this is what we're trying to detect here. So we look at in some sense we look at correlations of co-firings, and we build a complex which whose structure depends on those co-firings. So in some sense, instead of looking at the network with its usual architecture, we look at a graph and then a simplified complex whose structure depends on the co-firing. And we think that there is a lot of structure there. And in particular, those one-dimensional cycles, we can interpret them as some kind of shortcuts in the actual neural network. And those shortcuts happen to be more pronounced in networks which have been tampered.
Thanks.
More questions?
I have a question. Thanks for your talk. So I was wondering if you've considered using more than one pointwise distance measure simultaneously via weighting them. So I was thinking in like the text example, for example, maybe like a really long book about cats and a really long book about dogs, you actually want to be sort of more closely related than like a long book about cats and a tweet about cats. Although maybe a tweet about cats and a blog post about cats are like more similar. So I was thinking you could achieve that by using all the different distance measures that like correspond to some property that you care about, but then assigning different weights to them, and then you could like have a more complex model. So I was just wondering if you've like thought about that or known anyone who's thought about that.
Actually, I don't know. I mean, I think this is definitely a good idea. To what extent people do this, I actually don't know. The one reason why I don't know is because I also at some point realized that in this space of text mining and things like that, it's not clear what a good application of TDA is. Like, I think it's a very nice setup, which is why I presented this as a setup. But in terms of like a real application you could do there with TDA, it's not clear what it could be. So in some sense, at some point I stopped thinking about how you can measure things because it's also not clear, what kind of applications with TDA you can do there.
Yeah, thanks. That makes sense. Like having a specific use case in mind before applying, like what I talked about, totally makes sense.
Yeah, but what you suggested, I think it definitely would make sense. But I'm probably not the best person to ask. Like someone who actually does research in information retrieval could probably give you a much better answer.
Alkanon, please.
Hey, this is a question that's actually inspired by the last question, so maybe the answer will be similar. So there is this nice paper by Carlson and Memoli about sort of if you want a clustering algorithm that's functorial in a certain sense. There's a kind of uniqueness to it. And here you have a variety of ways of sort of taking a distance metric and sort of extending it. And there is a kind of functoriality that needs to be preserved and that it has to respect the structure of the complex. And I'm wondering is there a classification that you could make about what are the possible ways of extending things that are valid, or is it just wild? There's just too many.
I mean, so one thing I didn't talk about are those Bregman divergences. So this KL divergence is one member of the family of Bregman divergences, and there are infinitely many of them. They are uncountably infinitely many of them. Each of them is parameterized by a single strictly convex function, essentially. So from this perspective, you have a continuum of choices. If there is, I mean, it definitely would be nice to have like a classification or some kind of hierarchy of those distances. On the other hand, so one thing which I know from this information retrieval field is they have this adage that it's one of those fields where they have this kind of no free lunch theorems. Namely, they in this case it means that most probably there is no single, just like there is no single best clustering algorithm. There is also a supposedly no single best distance, just because they, each of them captures something else. So in some sense, you have to know what you're after. Otherwise, there is no objectively single best distance, I think.
Interesting. I guess it naturally leads, I don't want to ramble too much, to the question that there's sort of many questions of this flavor. Can there be 2 point clouds that have the same persistences for all these possible extensions? Because you now get a family of invariants, and then maybe you get an injectivity property. Maybe you want to consider many of them, but yeah, I'll let other people ask questions. Thanks.
More questions from folks?
If I may ask a question.
Of course, please.
Thank you for this presentation. I have one small question. Since you are working right now with, trying to extend this to information theory, and now you're using Kullback library divergence, have you tried other measures like mutual information or something like that? Have you thought about that?
Yeah, I actually haven't tried mutual information. So we work specifically with KL divergence because it is a Bregman divergence. So we actually have quite general results which apply to arbitrary Bregman divergences, and then KL is just one of them. And mutual information, I don't think, or I'm not aware of a generalization of mutual information, in a similar way. So in some sense, KL is interesting for us because there is this entire family of divergences, which also include KL. But yes, I agree that there are also other kind of similar distances which could be used instead, potentially. Yeah, that's a good question.
Great, thank you.
More questions? I have one, Hubert, just because I'm interested in divergences and these Fisher metrics, but I haven't fully made them my own yet. I was wondering if you could go to the slide where you have the idea from Gromov and Antonelli. So did I understand correctly that Gromov and Antonelli had an idea to take the KL divergence and turn it into a metric, which is called the Fisher metric? Is that correct, or is that incorrect?
Yes, I mean this was the point of this slide. Yes.
Okay. Cool. And so the KL divergence was sort of locally symmetric, but when you do this trick, it makes it globally symmetric as well.
Yes, but of course you get something which is, you know, which can be far away from KL. So in the end, the metric you did, this Fisher metric, it behaves very differently from the original KL divergence. And some of this is nice because, you know, it's a metric. In particular, it is symmetric. All the values are finite, unlike the usual KL, which you know, is for some pairs of points you would have infinite values, which is, you know, on the one hand it has a nice explanation, on the other it's kind of annoying when you want to compute those distances, and you know, and you hope that things won't crash. So you know, it's kind of a balance between nice mathematical properties and but also how much you can explain the measurements in terms of information theory.
Mm-hmm. Thanks, I appreciate it. Any final questions? Well, if not, thanks so much, Hubert, and let me stop the recording here.